Exploration and optimization of 3D integrated DRAM subsystem. Introduction. Exploration and optimization of 3D integrated DRAM subsystems involve designing and improving the performance of DRAM memory in a three-dimensional arrangement. This technology involves stacking multiple layers of DRAM dies on top of each other through silicon vias TSVs connecting the dies. In recent years, the demand for high-performance computing system has increased dramatically, and the 3D integrated DRAM subsystems have emerged as a promising solution to meet these demands. The purpose of this is to explore and optimize 3D integrated DRAM subsystem by discussing their benefits and exploring various optimization techniques to improve their performance. What is DRAM? Dynamic Random Access Memory, Dynamic RAM or DRAM, is a type of random access semiconductor memory that stores each bit of data in a memory cell, usually consisting of tiny capacitors and transistors, both typically based on metal oxide semiconductor MOS technology. DRAM chips are widely used in digital electronics where low cost and high capacity computer memory is required. One of the largest applications of DRAM is the main memory, colloquially called the RAM, in modern computers and graphic cards, where the main memory is called the graphics of memory. What is 3D integrated DRAM subsystem? 3D integrated DRAM subsystems are highly energy efficient DRAM subsystems for next generation 3D integrated SoCs, which will consist of SDRs or DDR 3D DRAM controller and an attached 3D DRAM cube with finite grain access and flexible wide I/O interface. Benefits of 3D integration. 3D integration offers several advantages over traditional 2D integration. Firstly, it offers high memory bandwidth and capacity per unit area, allowing for denser and more efficient memory subsystems. Secondly, it reduces the length of interconnects, which in turn reduces power consumption and latency. And finally, it enables the integration of heterogeneous technologies such as DRAM and logic on same chip, resulting in improved system performance and reduces system complexity. Optimization of 3D integrated DRAM subsystems. Optimizing 3D integrated DRAM subsystems requires a deep understanding of the various components and their interactions. Here are some general guidelines for optimizing 3D integrated DRAM subsystems. Firstly, system design. The system design plays a crucial role in optimizing the 3D integrated DRAM subsystems. System design should consider factors such as bandwidth, latency, power consumption, thermal management, and reliability of the subsystem. They should also consider the placement of memory controller, DRAM chips, and other components to optimize the signal integrity and minimize noise. Optimization of 3D integrated DRAM subsystems. System design. The system design plays a crucial role in optimizing the 3D integrated DRAM subsystems. System designers should consider factors such as bandwidth, latency, power consumption, thermal management, and the reliability of the subsystem. They should also consider the placement of the memory controller, DRAM chip, and other components to optimize the signal integrity and minimize noise. Second one, memory controller. The memory controller is responsible for managing the flow of data between the processor and the DRAM subsystem, and it is important to choose a memory controller that can handle the high bandwidth requirements of the system. The memory controller should also support advanced features such as error correction codes, ECC, page mode access, and burst transfers. And third one, DRAM chips. The DRAM chips are the heart of the subsystem and must be chosen carefully. System designers should consider factors such as capacity, speed, and power consumptions of the DRAM chips. They should also ensure that the DRAM chips are compatible with the memory controller and they can handle the high bandwidth requirements of the system. Thermal management. Thermal management is critical for 3D integrated DRAM subsystem. The high power density of the subsystems can lead to the thermal issues that can impact performance and reliability. Subsystem designers should consider techniques such as thermal vias, heat spreaders, and a liquid cooling to manage the temperature of the subsystem. Power management. Power management is another critical aspect of 3D integrated DRAM subsystems. Systems designers should consider techniques such as voltage scaling, clock gating, and power gating to minimize the power consumption of the subsystem. They should also consider dynamic voltage and frequency scaling (DVFS) to optimize the performance and power consumptions based on the workload. Sixth one, test and validation. Finally, it is important to thoroughly test and validate the 3D integrated DRAM subsystem. System designers should use simulations and modeling tools to predict the behavior of the subsystem under various conditions. They should also perform extensive testing to ensure that the subsystem meets the design specifications and can handle the workload. Exploration of 3D integrated DRAM subsystems. To explore 3D integrated DRAM subsystems, one need to consider the following aspects. First one, design consideration. A 3D integrated DRAM subsystems requires careful design considerations to ensure that it meets performance requirements while minimizing power consumption and cost. This includes the selection of appropriate DRAM chips, interconnects, and packaging techniques. Fabrication techniques. Fabrication of 3D integrated DRAM subsystems required advanced fabrication techniques such as a through silicon via TSV technology, wafer bonding, and a 3D stacking. Third one, system level integration. The integration of 3D integrated DRAM subsystem in a large system requires careful consideration of system architecture and its compatibility with existing components. And in conclusion, 3D integrated DRAM subsystems offer several benefits over traditional 2D integrated and can be optimized using various techniques to improve performance. The choice of the memory architecture, advanced memory management techniques, and advanced interconnection technologies such as through silicon vias TSVs can significantly improve the performance of 3D integrated DRAM subsystems as demand for high performance computing systems continues to grow. It is likely that 3D integration will become as increasingly important technology in future computing systems. Thank you.